There's something about staring up at the night sky that fundamentally changes how you think about your place in the universe. For most of human history, we looked up and saw only what was close, what was familiar, what belonged to us. The stars that dotted our heavens, the planets that graced our firmament. All of it seemed permanent, all of it seemed to obey rules we could predict and understand. But then came July of 2025, and with it came a messenger from the stars. Not the stars we know, but someone else's stars. Someone else's sun. And with that messenger came questions that science is only beginning to unravel. This is the story of 3I/Atlas, the third confirmed interstellar object ever observed by humanity. And what China's Tianwen-1 spacecraft saw when it looked upon this cosmic wanderer is forcing us to rethink everything we thought we knew about visitors from beyond our solar system. Let me set the stage for you, because context is everything in science. Every discovery exists within a landscape of previous discoveries, and to understand what makes 3I/Atlas so extraordinary, we need to understand what came before. In 2017, astronomers detected something moving through our solar system that didn't belong here. They called it Oumuamua, Hawaiian for a messenger from afar arriving first. And it truly was a messenger. It came screaming through our cosmic neighborhood at roughly 26 kilometers per second, following a trajectory that could only mean one thing. It had come from outside our solar system. That object was elongated, strange, almost cigar-like in appearance. It didn't behave like anything we had ever seen before. Some scientists marveled at its unusual properties. Its acceleration seemed to defy explanation, while others debated whether such an object should even be possible. The conventional wisdom of planetary formation suggested that big interstellar objects traveling alone through space shouldn't exist in any significant numbers. Yet there was Oumuamua defying that conventional wisdom, raising more questions than it answered. Then came 2019. A second interstellar object was detected, 2I/Borisov. This one was different. This was a comet, a real, active comet spewing water vapor and dust just like the icy travelers we know from the outer reaches of our own solar system. Borisov was more familiar, more predictable. It showed us that maybe, just maybe, the universe was following its own logical rules. Comets from other star systems would look and behave like comets from our star system. The laws of physics are universal, after all. This was reassuring. This was something we could understand. But then came 2025, and with it came something that didn't fit neatly into either category. On July 1st of this year, a telescope in Chile called ATLAS, the Asteroid Terrestrial Impact Last Alert System, detected something unusual streaking across the sky. It was faint, it was small, and it was moving impossibly fast, about 58 kilometers per second. The Minor Planet Center examined the trajectory, did the math, and reached an inescapable conclusion. This object was on a hyperbolic orbit. It wasn't bound to the sun, came from outside, and it would leave the same way. This was interstellar object number 3. They called it 3I/Atlas, following the naming convention that had become established with the previous 2 visitors. The 3I denotes it as the third confirmed interstellar object. Atlas denotes the facility that discovered it. And from that moment forward, the astronomical community was captivated. Every major telescope in the world turned its attention skyward. The Hubble Space Telescope observed it. The James Webb Space Telescope, with its infrared vision, peered at its composition. Ground-based observatories from Chile to Hawaii began collecting data. And somewhere in the constellation of Mars, orbiting above the Red Planet, a Chinese spacecraft named Tianwen-1 began preparing for something extraordinary. Now, I need to explain something about Tianwen-1 that makes what happened next so remarkable. This spacecraft was not designed to look at distant, faint objects. It was designed to study Mars. This camera, called HiRIC, the High-Resolution Imaging Camera, was built to examine the Martian surface with exquisite detail. But in early September of 2025, the Chinese Space Agency did something that most space agencies would never attempt. They looked at their orbiting spacecraft floating above Mars and asked a simple question. Could we use this camera, built for an entirely different purpose, to photograph something that would require a completely different kind of observational skill? Could we capture an image of an object that would be thousands of times fainter than anything we were designed to see? The answer required engineering ingenuity, careful planning, and an understanding of what was theoretically possible even if it wasn't theoretically optimal. The team running Tianwen-1 conducted simulation after simulation. They ran thousands of calculations. They tested their camera systems repeatedly, adjusting exposure times and imaging strategies. And they made a crucial realization. It was possible. Difficult, yes. Unlikely by normal standards, absolutely. But possible. The reason it was so difficult helps illustrate something fundamental about how telescopes work and what challenges astronomers face when observing distant objects. 3I/Atlas, moving at 58 kilometers per second through space, presented what we call a moving target problem. From the perspective of Tianwen-1, this object wasn't just dim, it was dim and moving rapidly. The relative velocity between the comet and the orbiter was about 86 kilometers per second. That's roughly 190,000 miles per hour of relative motion. Imagine trying to photograph a bullet with a camera designed to photograph landscapes, and you're starting to grasp the challenge. Moreover, 3I/Atlas is small. We estimate its nucleus, the solid, icy core at its heart, to be roughly 5.6 kilometers in diameter. That's about 3.5 miles. Put another way, if you placed it on a map of the United States, you'd struggle to find it without zooming in significantly. And this small object is approximately 10,000 to 100,000 times darker than the features on the Martian surface that Tianwen-1 was designed to image. We're talking about an object that is incredibly faint, incredibly small, and moving at velocities that seem almost incomprehensible. Yet, on October 3rd of 2025, Tianwen-1 succeeded. From a distance of approximately 28.96 million kilometers, the spacecraft's high-resolution camera captured images of 3I/Atlas as it made its closest approach to Mars. The images were fuzzy, yes. They were not as clear as we might hope, but they existed. And when the China National Space Administration released these images to the world in early November, the scientific community sat up and took notice. Because something was visible in those images that raised profound questions about what this object actually is. Now, let me explain the cosmic context here, because this is where things get interesting. You see, we live in an era of unprecedented astronomical observation. We have more tools than ever before to study the heavens. We have space telescopes that can see infrared light, ultraviolet light, and the visible spectrum. We have ground-based observatories so sophisticated that they can measure the precise movement of distant stars. And yet, with all these tools, all this technology, all this accumulated knowledge, we are still being surprised. Regularly, profoundly. 3I/Atlas is one of those surprises. Because when astronomers began analyzing the early observations, when they started compiling the data from multiple telescopes and multiple observatories, they found something that didn't quite fit the standard model of how comets should behave. Let's talk about composition for a moment, because composition tells us so much about an object's origins. In our solar system, comets are built largely from water ice, with mixtures of other volatile compounds, methane, ammonia, carbon dioxide. When these comets get close to the sun, they heat up, and the ice begins to sublimate. You get water vapor rising into space, dust being ejected, and the characteristic tail that makes comets so visually distinctive. We've observed this pattern thousands of times. It's reliable, it's predictable, we understand it. But 3I/Atlas doesn't follow that pattern. Spectroscopic observations, measurements that allow us to determine what an object is made of by analyzing the light it emits or reflects, revealed something surprising. The composition of this comet's coma, the gaseous envelope surrounding its icy nucleus, was dominated by carbon dioxide and carbon monoxide. That's unusual in itself, but here's where it gets really interesting. The ratio of carbon dioxide to water was approximately 8:1. 8 parts carbon dioxide for every 1 part water. Among comets, this is extraordinarily rare. We've observed thousands of comets in our solar system, and while some have unusual compositions, a CO2 to H2O ratio of 8:1 is something we almost never see. Now, there are explanations for this. Reasonable explanations. Legitimate scientific explanations. Some researchers suggest that 3I/Atlas might have formed in a region of its parent star system where carbon dioxide ice was abundant, perhaps near what we call the CO2 ice line, where temperatures are cold enough for CO2 to freeze, but the star's radiation is too intense for water ice to survive. This would be evidence that planetary systems around other stars have different structures and different chemical compositions than what we see around our sun. Which, by the way, is exactly what we would expect. Planetary systems vary. The physics is the same everywhere, but the specific outcomes depend on initial conditions. And yet, there's always an "and yet" in science, isn't there? The low water content created another puzzle. 3I/Atlas, being an active comet that was clearly outgassing, ejecting material into space, was doing so with minimal water vapor involved. The gas plume surrounding the object contained only about 4% water by mass. For comparison, comets we know from our own solar system typically show much higher water content. In fact, the dominant component of most cometary activity is water. It's what powers the jets. It's what creates the coma. The fact that this object was being so active with so little water present raised questions about what exactly was driving that activity. And there was something else, something even more unusual. When Hubble first observed the comet, it was red. All objects appear some color based on what light they scatter and absorb, and most comets, with their dust-covered surfaces, appear reddish to our eyes. As 3I/Atlas approached the sun, that should have continued. Red dust should scatter red light more efficiently than blue light. This is basic physics. It's why sunsets are red, because red light is scattered less in the atmosphere as it travels at a shallow angle through the sky. You would expect the same from a comet. Heat it up, sublimate more ice, eject more dust, and it should look even redder. But something extraordinary happened. As this object approached perihelion, its closest point to the sun, which would occur on October 29th, something changed. Dramatically, images taken by multiple space-based observatories captured it emerging from behind the sun not just brighter, but visibly bluer. Not blue-green, not slightly blue, distinctly blue. Bluer than the sun itself. Now, for those of you listening to this and thinking, well, that's interesting but not necessarily shocking, let me explain why this is actually profound. The sun's photosphere, its visible surface, has a temperature of about 5,800 Kelvin. That's roughly 5,500 degrees Celsius or 10,000 degrees Fahrenheit. Blue light is emitted by objects that are hotter than red light. The sun appears yellow-white because it's emitting light across a broad spectrum. But if something is bluer than the sun, it's either hotter than the sun or it's emitting light for some reason other than thermal radiation from a normal surface. 3I/Atlas is an icy comet nucleus, probably only a few kilometers across. Its surface, warmed by the sun but still extremely cold in the context of nearby space, should be far colder than the sun. And yet it appeared bluer. This is what we call an anomaly, not an error, not a measurement problem. A genuine, documented anomaly that doesn't fit our models of how comets should behave. The brightness surge accompanying this color shift was equally unusual. Most comets follow what we call a light curve, a predictable pattern of brightness variation as they approach and recede from the sun. We have mathematical models that describe this light curve. They're based on the physics of ice sublimation, the mechanics of dust ejection, and the way solar radiation affects cometary behavior. These models work remarkably well for solar system comets. We can predict how bright a comet will be at any given distance from the sun with reasonable accuracy. 3I/Atlas violated those predictions. It brightened faster than any known comet in our solar system. Much faster. The rate of brightness increase near perihelion was extraordinary, suggesting an energy output that didn't match what we would expect from a simple icy object warming up in the sun's heat. This is when things got really interesting in the scientific community. Because once you have multiple anomalies, unusual composition, unexpected color shift, rapid brightness increase, you start asking different questions. Not what is this, but what could this possibly be? Now, I need to be careful here. There's a difference between genuine scientific mystery and speculation. And there is genuine mystery here. But there is also speculation that has entered into the popular discussion of 3I/Atlas. Some of this speculation is grounded in legitimate physics. some of it is less so, and I think it's important for us to acknowledge both. One of the most serious scientists to publicly discuss alternative interpretations of 3I/Atlas is Avi Loeb, an astronomer at Harvard University. Loeb has a long history of asking unconventional questions and challenging mainstream thinking. He's known for his work on the Galileo Project, which focuses on searching for technological signatures in the cosmos. He's also become somewhat famous, or perhaps infamous depending on your perspective, for his willingness to discuss the possibility that some astronomical anomalies might have artificial origins. When 3I/Atlas was first observed, Loeb began cataloging its unusual properties. Initially, he identified 8 anomalies, properties that deviated from what we would expect for a natural comet. Then, after observing the blue color at perihelion, he added a 9th. In a series of blog posts and published analyses, he has suggested that the combination of these anomalies might indicate that 3I/Atlas could be an engineered object, possibly a probe or spacecraft of some kind. Now, before you dismiss this out of hand, I want you to understand that Loeb is not being anti-scientific. He's not denying the possibility of natural explanations. What he is doing is applying a principle of logic that goes back to philosophers like David Hume. If you observe something unusual that violates multiple expectations, you should consider all possible explanations, including those that might seem initially improbable. Let's look at some of these anomalies. I mentioned the composition already, the high CO2 ratio and low water content. Loeb has suggested that this composition could result if the object is not a natural comet but something else entirely. Perhaps an object that has traveled through the cold of interstellar space, accumulating a layer of dust and ice on its surface, but whose internal structure is fundamentally different from a comet. Then there's the matter of the jets. 3I/Atlas exhibits jets, narrow streams of gas and dust, that are remarkably well collimated. Collimated means they stay tightly focused, maintaining their direction and intensity over large distances. We see jets in nature from astronomical sources like active galactic nuclei, where supermassive black holes eject material along their rotation axes. We see jets from young stars. We see jets from comets as well, particularly when activity is concentrated in specific regions. But the jets from 3I/Atlas are unusual in their persistence and directionality. We observe jets pointing toward the sun and jets pointing away from the sun simultaneously. The object is rotating. It has a rotation period of about 16 hours. Yet the jets maintain their orientation across distances of millions of kilometers. For a natural comet, this would require an exceptionally large surface area to absorb enough solar radiation to sublimate enough ice to fuel these jets. The geometry doesn't work well. If, on the other hand, these jets were powered by something other than sublimating ice, if they were hypothetically some kind of thruster or propulsion system, then their properties would make much more sense. They would be tightly controlled. They would maintain their orientation regardless of rotation. They would be powered by stored energy rather than solar heating. Again, I want to emphasize, this is hypothesis, not conclusion. This is speculation based on observations, not certainty based on evidence. But it illustrates something important about how science progresses. We observe, we measure, we note discrepancies between observation and theory, and then we brainstorm explanations, keeping our minds open to possibilities while maintaining rigorous standards of evidence. Another anomaly Loeb has discussed involves the trajectory of 3I/Atlas. The object is approaching our solar system on a trajectory that is remarkably well aligned with the ecliptic plane, the plane in which Earth and the other planets orbit around the Sun. The probability of this happening by chance is quite low, perhaps on the order of 0.2 to 1%. For someone considering non-natural explanations, this remarkable alignment is suggestive. It could indicate that the object was directed toward us, rather than arriving by pure chance. Of course, this can also be explained naturally. Interstellar space is large, and the objects passing through it are numerous. Some of those objects will, by pure chance, be aligned with our ecliptic plane. It would be statistically surprising but not impossible. And confirmation bias is a real phenomenon in science. We humans tend to notice patterns that support our preferred explanations while overlooking patterns that don't. Let me also mention the issue of the object's fragmentation or structure. Early observations suggested that the surface of 3I/Atlas might be highly fragmented, almost like shattered glass or fractured sheets. This would be unusual for a comet, which typically has a relatively cohesive structure, at least on the surface. If the object is not a simple icy nucleus but something more complex, perhaps something with a different internal structure, then fragmentation wouldn't be unexpected. And there's one more property that has captured attention: the polarization of light reflecting off 3I/Atlas. Polarization is a property of light waves that describes the orientation of their oscillation. Different materials reflect light with different polarization signatures. When astronomers measured the polarization of light from 3I/Atlas, they found something remarkable: extreme negative polarization with an inversion angle that is unprecedented. No other comet or asteroid in our solar system shows this property. What does this mean? It could indicate surface composition unlike anything we've seen before. It could suggest a surface structure that is extremely fine-grained, almost like powder. Or, hypothetically, it could indicate a surface that is partially reflective but also partially absorptive in a way that mimics the properties we would expect from certain engineered materials. Now, I'm presenting all of this not to convince you that 3I/Atlas is an alien probe. I'm presenting it to show you what legitimate scientific inquiry looks like when confronted with genuine anomalies. We observe, we measure, we hypothesize, we consider multiple explanations. Some of those explanations will be more likely than others based on the evidence we have, but we don't dismiss the less likely ones out of hand. We ask what additional observations would help us distinguish between competing hypotheses. And this is exactly what the scientific community has been doing. Multiple telescopes have observed 3I/Atlas from multiple angles. Radio telescopes have measured its emission. X-ray observatories have examined it. The data from all of these observations is being compiled, analyzed, and discussed. Eventually, consensus will emerge about what this object is. But right now, we're in a phase where legitimate uncertainty remains. This brings us back to China's Tianwen-1 and those images released in early November of 2025. When the images were first released, there was immediate interest in what they showed. The images themselves were not high resolution. Remember, these were taken by a camera designed for an entirely different purpose. But they showed something clear. The object had a bright nucleus surrounded by an extended coma stretching between 3,100 and 6,200 kilometers across. The visible structure showed characteristics consistent with cometary activity: outgassing, dust ejection, a halo of material surrounding the central body. And yet, some observers noticed something in these images. The surface appeared to have a particular quality to it. Some described it as fragmentary, as if it were composed of discrete chunks rather than a cohesive whole. Others noted that the images seemed to show something unusual about the structure of the coma itself: asymmetries and features that didn't quite match typical cometary morphology. Now, here's where I want to be very careful about the difference between what the images show and what we interpret them to show. The images from Tianwen-1 are not high-resolution enough to reveal fine detail on the surface of 3I/Atlas. They're not clear enough to definitively determine whether the surface is fragmented or smooth, whether it's composed of multiple pieces or a single object. What they do show is the overall structure and the coma surrounding it. But that overall structure, combined with data from other observatories, tells us something interesting. The object is clearly active, clearly outgassing and ejecting dust. The level of activity is consistent with what we would expect from a comet being heated by the sun. The coma is visible, the dust is present, the physics of cometary outgassing seems to be at work. What's less clear is whether the object is a single cohesive nucleus or something more complex. Whether it's a monolithic icy body or a collection of smaller fragments held together loosely. Whether its interior structure matches what we would expect from a comet or something more unusual. This distinction matters because it affects what hypotheses we should consider. A natural comet would likely show certain expected properties. An object with a different origin or structure might show different properties. By carefully examining the images from Tianwen-1, by comparing them with observations from Hubble, from James Webb, from radio telescopes and X-ray observatories, astronomers can begin to narrow down what 3I/Atlas actually is. What I find remarkable about this entire situation is how it illustrates the progress of science in the age of rapid communication and global collaboration. 100 years ago, the discovery of an interstellar object would have been a significant scientific achievement, but it would have taken months or years for all the world's observatories to compile their observations and publish their analyses. Now, in 2025, we have images from Chinese space probes, data from American space telescopes, observations from European observatories, and measurements from ground-based observatories all over the world. All of it is being analyzed in real time. All of it is being discussed. All of it is contributing to our understanding of this object. But it also illustrates something else: the profound realization that with more data, more observations, and more analysis, sometimes we don't get clearer answers. Sometimes we get more questions. Because the universe, I have learned, is far more diverse and strange than any of our models predict. Let me tell you something about how my career has evolved. When I was starting out in astronomy, we had a fairly clear picture of how solar systems form, what kinds of objects can exist, what kinds of orbits are possible. We had models. We had predictions. And those models and predictions worked pretty well for the solar system we knew. But then we started discovering exoplanets, and those exoplanets started violating all our predictions. We found gas giants in close orbits around their stars, something our models said shouldn't happen. We found planets in binary star systems. We found ultra-short period planets. Each of these discoveries required us to revise our understanding of planetary system formation and evolution. And now, with interstellar objects, we're seeing a similar pattern. Each of the three objects we've observed, Oumuamua, Borisov, and 3I/Atlas, is different. Different shapes, different compositions, different behaviors. This tells us that interstellar space is filled with far more diverse objects than we initially hypothesized. The universe is more creative than we were. So where does this leave us with 3I/Atlas? I think the honest answer is we're not sure. We have observations. We have data. We have multiple hypotheses. The mainstream scientific view is that this is a comet, a natural object with unusual but not impossible properties. The composition can be explained by its origins in a different planetary system. The brightness surge can be attributed to unusual ice sublimation behavior. The color shift might result from the composition of the dust being ejected. The polarization can be explained by unique surface properties. These explanations are reasonable. They're scientifically sound. They don't require anything outside our understanding of physics. But they are not certainties. They are the best explanations we have based on available evidence. And science progresses by gathering more evidence. This is why the images from Tianwen-1 matter. Not because they definitively answer the question, what is 3I/Atlas? But because they're one more piece of the puzzle. They're data points from a unique vantage point, from Mars' orbit, closer to the object at closest approach than any other facility except the orbiters also at Mars. They give us a different perspective on the object, and perspective in science is everything. What we can say with confidence is this: 3I/Atlas is genuinely unusual. Its composition is unusual. This behavior is unusual. Its properties are, by the standards of objects we've observed before, anomalous. Whether those anomalies are the result of natural processes we haven't fully understood, or whether they indicate something more exotic, is a question that will continue to refine as more data becomes available. There's also something deeply human about this situation. We're encountering something we don't fully understand, and we're asking big questions about it. Some of those questions are scientific. What is the composition? What is the size? What is the density? But some of them are more philosophical. Could this be a message from another civilization? Could it be a probe? Could it be something our current models of physics don't adequately account for? These are not unscientific questions. They are questions that emerge when we confront genuine mystery. And genuine mystery should be approached with both intellectual rigor and openness to possibility. The observations will continue. More data will come in. Hubble will observe 3I/Atlas again as it recedes from the Sun. James Webb might capture additional spectroscopic data. Radio observations will continue to measure its composition. Ground-based telescopes will track its motion. And eventually we'll know more. perhaps much more. There's also something hopeful about this, because what 3I/Atlas represents is proof of concept. Proof that we can observe interstellar objects when they pass through our neighborhood. Proof that we can gather data about them, learn from them, and let their characteristics reshape our understanding of the universe. Proof that we're living in an era when international space agencies can collaborate, when the Chinese Space Agency can use a Mars orbiter in an unexpected way to contribute to humanity's understanding of the cosmos. In the coming years, we expect more interstellar objects to arrive. The estimates suggest that several should pass through our solar system every century. Some will be easier to observe than others. Some will arrive when we have better instruments available. And with each one, we'll learn more. We'll refine our models. We'll answer some questions and generate new ones. This is how science works. This is how human knowledge expands. Not through sudden revelation, but through patient observation, careful analysis, and a willingness to revise our understanding when evidence demands it. 3I/Atlas, with all its unusual properties and its mysterious behavior, is teaching us something important about the universe. It's teaching us that the cosmos is far more diverse than we realized. It's teaching us that our models, for all their sophistication and predictive power, are still incomplete. It's teaching us that wonder and mystery are not things we outgrow with scientific advancement. They're things we encounter again and again as we push the boundaries of our knowledge. When you look up at the night sky, when you contemplate the vast distances between stars, when you consider the possibility that objects are right now traveling between solar systems, you're contemplating something profound. You're contemplating a universe that is simultaneously vast and intimate, ancient and dynamic, knowable and mysterious. 3I/Atlas is out there now, having made its closest approach to the sun, beginning its long journey back into the depths of interstellar space. It will fade from our observatories eventually. It will become too faint to see, even with our best instruments. And then it will continue its journey toward the next star system, the next solar system, carrying with it secrets that we may never fully unravel. But for a brief moment in the history of humanity, we had the opportunity to observe it, measure it, analyze it, and ask questions about it. We had telescopes pointed at it from Earth and from space. We had a spacecraft orbiting Mars that turned its camera toward this unexpected visitor. We had international collaboration focused on understanding this object. And in doing so, we expanded the boundaries of human knowledge. We contributed to the great project of understanding the cosmos that our species has been engaged in since we first looked up at the stars and wondered, what is that? Where did it come from? What does it mean? That, to me, is what makes 3I/Atlas so significant. Not necessarily what it is, whether it's a natural comet or something more exotic, but what it represents. It represents our capacity as a species to observe, to measure, to question, and to grow. It represents our curiosity about the universe and our commitment to understanding it. It represents the idea that even in an era of great technological sophistication, the cosmos can still surprise us. The universe can still reveal mysteries. Wonder can still grip our minds when we confront something genuinely unknown. Now, let me turn to something that's been discussed in some quarters, and I want to address it directly. There are those who have suggested that NASA's relative quietness about 3I/Atlas compared to China's aggressive release of images indicates some kind of deliberate withholding of information. That NASA discovered something that they didn't want to reveal. That there's a conspiracy of silence about what this object really is. I think it's important to address this critically and honestly. What actually happened is this: NASA did observe 3I/Atlas with its Mars Reconnaissance Orbiter, specifically with the HiRISE camera, which has higher resolution than China's Tianwen-1 camera. High-rise images would have offered superior detail. However, the release of those images was delayed due to the US government shutdown that occurred in October 2025. Federal agencies, including NASA, were not operating at full capacity during this shutdown. Data couldn't be processed and released through normal channels. This was not a decision to withhold information. It was a consequence of bureaucratic circumstance. Meanwhile, China's space agency faced no such constraint. They processed their data, verified their results, and released them to the public. This created an optic situation where it appeared that China was more transparent and forthcoming than NASA. In reality, both agencies were doing their jobs with the resources available to them. Now, this does raise an interesting point about how scientific information is released and communicated to the public. In an era of rapid information flow, when data can be transmitted around the world in seconds, the timing of releases matters. It affects public perception. It affects how information is understood and discussed. But it doesn't change the underlying reality that 3I/Atlas is a genuine object with genuine unusual properties that warrant investigation and discussion. Let me also address the speculation about potential artificial origins more directly, because I think it deserves a thoughtful discussion. The idea that 3I/Atlas could be an artificial probe or spacecraft is, on its face, scientifically possible. We know that technology can exist in the cosmos because we created it. We've sent spacecraft to the planets. We've put rovers on Mars. If we can do it, then other civilizations, potentially far more advanced than us, could do it as well. So the hypothesis is not logically impossible. However, it faces some significant hurdles from a probability standpoint. The universe is vast. The probability of an artificial object from another solar system randomly arriving in our neighborhood at precisely the time we've developed the technology to detect it is extraordinarily low. This is sometimes called the luck problem in SETI discussions. If advanced civilizations are deliberately sending probes throughout the galaxy, it seems unlikely that we'd intercept one by chance at the exact moment we've developed the capacity to detect it. That said, there are scenarios where this becomes more probable. If advanced civilizations deliberately sent probes to every star system within some region of the galaxy, then we would inevitably encounter one eventually. If we're living in an era where multiple civilizations have reached spacefaring status and are exploring the galaxy, then encounters become more likely. These are not impossible scenarios. They're just less likely than simpler explanations that don't require multiple independent advanced civilizations to have sent probes to our solar system. So from the standpoint of parsimony, the principle that we should prefer simpler explanations when evidence is ambiguous, the most likely explanation is still that 3I/Atlas is a natural object with unusual but not impossible properties. But I also want to acknowledge that this principle of parsimony shouldn't be allowed to foreclose inquiry or prevent us from asking interesting questions. If observations continue to accumulate that suggest artificial characteristics, then we should be willing to take those suggestions seriously. The hypothesis of artificial origin shouldn't be dismissed out of hand simply because it seems unlikely. Rather, it should be held to the same standards of evidence as any other hypothesis. And this is where the distinction between scientific skepticism and closed-mindedness is crucial. Scientific skepticism means demanding good evidence before believing extraordinary claims. It doesn't mean refusing to consider possibilities that seem unlikely. Closed-mindedness means dismissing ideas without proper consideration. We should strive for the former and avoid the latter. So where does this leave us with 3I/Atlas and China's Tianwen-1 images? I think it leaves us in a position of honest uncertainty combined with the excitement of discovery. We have an object with unusual properties. We have images from a unique vantage point. We have data from multiple observatories. And we have room for future discovery and understanding. What I find most compelling about this entire situation is how it demonstrates the power of science to confront genuine mystery without either dismissing it or descending into baseless speculation. We can acknowledge the genuine oddities of 3I/Atlas. We can discuss the different hypotheses that might explain those oddities. We can continue to gather evidence and refine our understanding. And we can do all of this while maintaining intellectual rigor and honest acknowledgement of uncertainty. This is the method by which human knowledge advances, not through sudden revelation or dogmatic assertion, but through patient inquiry, careful observation, and willingness to revise our understanding as evidence demands. 3I/Atlas, in the end, may turn out to be exactly what most mainstream scientists think it is: a natural comet with unusual properties born in a different planetary system, shaped by different conditions, composed of different materials than those we typically encounter. This would still be remarkable. It would still expand our understanding of what kinds of objects exist in the galaxy and how diverse the population of small bodies can be. or it might turn out to be something else. Some of the anomalies might have explanations we haven't yet conceived. More data might reveal patterns that current observations haven't shown. Future investigation might confirm hypotheses that seem speculative now. The point is that we don't know yet, and the fact that we don't know is what makes this so exciting. We're living in an era where the universe can still surprise us, where despite all our technology and all our accumulated knowledge, the cosmos can present us with mysteries. That's not a failure of science. That's a success. That's what science is supposed to do. Push back the boundaries of the unknown and reveal ever more about the universe we inhabit. Let me bring this back to something more personal and philosophical, because I think there's something important here about how we relate to the cosmos. When I was young, the universe felt large in an abstract way. I knew intellectually that the distances were vast, that the numbers involved were incomprehensibly large. But it didn't feel real. It was facts and figures in a textbook, not something that gripped my understanding. But then, as I got older, as I worked in astronomy and studied the cosmos, something shifted. The vastness stopped being a number and started being a genuine reality. When I think about the distance to the nearest star, when I calculate how long it would take light to travel between stars, when I consider the age of the universe and the incomprehensible expanse of cosmic time, I feel it. Not just intellectually understand it, but feel it in a way that affects my perspective on everything else. And then you encounter something like 3I/Atlas, and it all suddenly becomes very concrete and very real. This object is actually here. This messenger from another star system is actually passing through our cosmic neighborhood. We can actually observe it. We can actually gather data about it. We can actually ask questions about what it is and where it came from. That brings home, in a way that no amount of abstraction ever could, that we are inhabitants of a dynamic, changing cosmos. That the space around us is not empty and static, but filled with objects in motion, some of them from other star systems. That we are living at a time when we have the technology to detect these visitors and learn from them. And that creates a sense of wonder and responsibility. Wonder because the universe continues to surprise us. Responsibility because we're now at a point where we can ask meaningful questions about cosmic objects and actually gather data to answer those questions. This is part of why I find the story of 3I/Atlas so compelling. It's not just an interesting astronomical object, though it is that. It's a reminder of what's possible when human curiosity meets technological capability. It's a demonstration of what science can accomplish when multiple nations collaborate and contribute their resources and expertise toward a common goal of understanding. China's Tianwen-1, orbiting Mars and originally designed to study the red planet, turns its instruments towards something unexpected and succeeds in capturing the image. NASA's various space-based observatories contribute their data to the international pool of knowledge. The European Space Agency's Mars orbiters add their perspectives. Observatories around the world contribute ground-based observations. And from all of this data, from this international collaboration, emerges a more complete picture of this mysterious object. That's science at its best. That's how we learn about the universe. That's how we push back the boundaries of the unknown. So as we wrap up this discussion of 3I/Atlas and what China's images revealed, I want to leave you with this thought. The next time you look up at the night sky, when you see the stars scattered across the darkness, remember that the space between those stars is not empty. There are objects moving through it. Some of those objects are from our solar system, ejected into interstellar space by gravitational encounters with planets. Some of them are from other solar systems, scattered into the galaxy by unknown processes, traveling through the cosmic void for billions of years. And occasionally, by the laws of chance and the vast scope of the universe, one of those objects passes through our neighborhood, and we get to observe it. We live in an era when we can see those objects, when we can gather data about them, when we can ask questions about what they are and where they come from, when we can collaborate internationally to understand them better. That's remarkable. That's special. That's worth celebrating. 3I/Atlas, with all its mysteries and anomalies and unusual properties, is part of a larger story. The story of how human beings, despite living on a small planet orbiting an ordinary star, have managed to understand much about the universe and continue to expand that understanding every day. The story of how curiosity and inquiry can overcome obstacles and reveal truths about the cosmos that seem impossible when you first encounter the challenge. This is the story that science tells. This is the progress of human knowledge. And 3I/Atlas is another chapter in that ongoing story. The comet will fade from our observatories. It will continue its journey into the depths of space. It will eventually become so distant that even our most powerful telescopes won't be able to detect it. And it will carry its secrets with it, at least for now. But what it has revealed to us, what it has taught us about the diversity of objects in the cosmos and the capabilities of our observatories and the power of international collaboration, will remain. And somewhere, in years or decades or centuries to come, another interstellar object will arrive. We'll observe it, we'll measure it, we'll ask questions about it. And through that inquiry, we'll continue the great human project of understanding the universe. That's what makes discoveries like 3I/Atlas significant. Not necessarily what they answer, but what they reveal about what we're still learning, what we still don't understand, and what remains to be discovered in the vast cosmos that surrounds us. Thank you for joining me on this exploration of 3I/Atlas and what China's remarkable images have revealed about this cosmic visitor from the depths of interstellar space. Keep looking up, keep questioning, keep wondering, because wonder is not the opposite of science. It's the beginning of it. What we've witnessed with 3I/Atlas is more than just an astronomical discovery. It's a demonstration of how science evolves, how international cooperation advances human knowledge, and how the universe continues to hold mysteries even in an age of sophisticated telescopes and advanced technology. Whether 3I/Atlas proves to be a natural comet with unusual properties or something more exotic, it serves as a reminder that the cosmos is far more diverse and complex than any single model can predict. The images captured by China's Tianwen-1 spacecraft represent a triumph of engineering, determination, and human ingenuity. They represent our species' drive to understand the universe and our willingness to adapt, innovate, and collaborate to push the boundaries of that understanding. As we continue to observe and study this remarkable object, as we gather more data and refine our models, we're participating in an ancient human endeavor, the pursuit of understanding our place in the cosmos. 3I/Atlas will eventually fade from view, continuing its journey through the vast emptiness of space. But the knowledge it has given us, the questions it has raised, and the sense of wonder it has inspired will continue to resonate. This is the true value of discovery, not merely the answers it provides, but the insights it offers into the complexity and beauty of the universe and our capacity to comprehend it. The story of 3I/Atlas is still being written. New observations will reveal new details. Future analysis will deepen our understanding. And perhaps, in years to come, we'll look back on this moment, when a Chinese spacecraft orbiting Mars turned its camera toward an unexpected visitor from the stars, and recognize it as a pivotal moment in humanity's understanding of the cosmos. For now, we know what we know and we acknowledge what we don't. We observe, we measure, we question, and we remain open to discovery. And in doing so, we honor the spirit of scientific inquiry that has always driven human progress. The cosmos awaits our continued exploration. And with objects like 3I/Atlas to guide our investigation, the future of astronomical discovery looks as boundless and mysterious as the universe itself.